So let's begin our lecture. First, I want to solve some of last day's problems. And also, before that, I want to solve the problem from the string contest, problem D. Has anyone solved it? The problem was finding that whether for each cyclic shifter of our string is the prefix function greater than 0 or no. Has anyone solved it? So this problem has a great idea. I couldn't solve it neither. I think this idea will come handy in many problems. So basically, I told you in last session that when we want to check that whether there exists a string in a cyclic shift which is a prefix and also a suffix, we can see that this suffix appears here too. So we can count by these, but how? If this prefix and suffix, they both have the length, L, if I go through my string with indexes that are divisible by L, and I mean index 0, index L, index 2L, and so on, I can see that if these both characters should be equal, I can see that how much can I extend this from the right with a simple LCP with suffix array. And I can also see that how much I can extend it from the left with a suffix array and the reverse string. Since in the reverse strings, both of these are suffixes. And when I see that between two consecutive indexes which are divisible by L, I can find that there is a length at which these are in common. And if this length is greater than this L itself, just like this, I can see that here at this point I have a prefix which has a suffix, and in the next point too, until the last point which they are in common. There is a basic calculation to find the range, but I can find a range which for these suffixes there exists a prefix that has a suffix before that, and hence that has a suffix equal to its prefix. So basically the solution is to, for all of different lengths, go through all indexes that divide that length and find the LCP backward and forward with the next index, and then find the range which we can ensure that within this range we have a prefix function greater than 0. And you can add this range like a partial sum or something. This is the idea. And we can prove that this is correct, because if there exists an L here, which I mean there exists a prefix function for this cyclic shift which is greater than 0, if this is the length of L, I will find it through the iteration with length L. Because the indexes will be something like this, and if I extend from both sizes, I will find that this index is within the range that has suffix equal to prefix. So, anyone has any question? And basically, with this idea, the solution runs in the order of n log n squared. Because going through all multipliers of L for all L's takes n log n time, and finding the LCP is log n, and also we can do this in constant time. I think for passing the time limits, I myself had to do this with constant time, and maybe without another log. So that's the solution. Now back to last day's problem. I thought that problem K will be solved by more people, so I will tell you the solution. The problem said that we have, I think, some points in 3D, and we want to group these points into two partitions, and for each of those we find their mean point, and we want to, and for each of the groups, I think we want to find I don't know if the mean point is P. For each group we find this value, I think. And then we want for some of those two groups, this value become minimum. Am I right? And by this I mean dotting the value of this vector by itself. So this was the problem. Let me check. I think it's right. So I think the first observation to this problem is that basically these two groups in the space are separated. So if I find the convex hull of the first group and the convex hull of the second group, they don't have any intersection. Because we can say that if they have an intersection, just erase that intersection, move that point to the other group, and the answer will decrease. So with knowing this observation, we now should find all possible divisions of the points. And by that, we can use the idea that when those two convex polyhedrals are divided and don't have any intersection, there exists a plane that separates them. And I can move the plane in such a way that it intersects with at most 3 points of these two. Do you agree with that? So if not, I can move until it hits a point in the space. So by that I mean I can fix my plane for every 3 points in the space, or every 2 points, or every 1 point. But we can prove that if this is 1 point, we can move that to find the second point, and move that to find the third point, and fix this plane in the space. So by fixing the plane in the space, just like we might have 3 points in the space, since it's a plane, we can find all of the points on the right side and the left side of this plane in the space, using a 3D cross value. And yet the problem is not solved. We can't say that these points belong to which of these two groups. So we might have 8 possible configurations that, I mean by 8, each of them has 2 options, that these points belong to which of these groups. So basically, after fixing these 3 points and doing all of the configurations, we can find the values and take the minimum one. But the complexity is not good. And also, we should take care of some corner cases, such that maybe in one group we only have 1 point, and we should handle these cases. Because I'm not sure, maybe with taking all 3 points we cannot handle all of the cases. Like the case we have only 2 points. So we can handle this separately, but how can we do this faster? And the idea that I used, I'm not sure, I don't have any reason that it's fine or no. Before that, let me tell you the complexity here we have. The complexity here is n to power of 3 divided by 6, because the order here doesn't matter, multiplied by 8, and if I'm right, the n was 1,000. 2,000? Oh, 100. So it's n to power of 4. Am I right? We have n to power of 3 different cases for selecting these 3 points, and a linear time to find the values. And it doesn't fit in time. The idea that I used was that just consider these 2 groups without adding these 3 points, and if the value is greater than the current value we have, don't go through these cases at all. Because when without these points the value is greater, adding these points only adds a value.
I think that fits in time. My first solution got that it was 10 to the 4th and got 200 milliseconds.
So maybe you're right, but But a friend of mine couldn't accept it with this approach. So maybe with doing this fast we can achieve this again. So that's the idea to solve it. So I couldn't solve problem F. I'm sorry about that. If anyone has any idea about that, please tell me too. But I thought a lot about it, but I couldn't solve it. So now for problem E. I think only one team managed to solve this problem. The problem said that we have n intervals, and we have made a graph out of these intervals, that two intervals correspond to two vertices, and they share an edge between each other. If they intersect, their intervals intersect at any point. And the problem wanted us to find for each value of k, by removing at most k intervals, how many components can I have in the graph? What is the maximum number of components can I have in the graph by removing k intervals? By removing exactly k intervals. So I at first thought that I can solve this with flow, but I was completely wrong. And the solution is simply not a simple one, but it's a dynamic programming solution. So I will sort the intervals based on their endings. And then define a dynamic programming on it. By that I mean I define dp of I and j. It means that if I want to have, if I go through only the first I intervals sorted by their endings, and I want to have j different components, what is the maximum number of intervals can I have to achieve that? I'm only going through the first I intervals, and I want to have j components that are not connected. What is the maximum number of intervals can I have in this graph that contains like j different components? So basically I'm counting the number of intervals that I have. It's somehow equivalent to the number of intervals that I should remove, but counting this one is a lot easier. And having this value, I can solve the problem. Do you all agree that if I have the value of this dp at the end, I mean that at the end I know that for having k components, I can have at most dp of n and k intervals. So basically n minus this value will become the minimum number of intervals that I should remove to achieve that. So how can I update this value and find the value for dp? Consider that the ith interval, I don't want to use this interval. So the solution for my dp1 solution is the dp of not using this one. So, and the next one is that I want to have this interval. And a little thing that I want to mention is that I think if two intervals have the same ending, I will put this first and then this one. I think it's better. So now I have this interval and this is in my graph. It's you can think and give me your idea how can I update this if I have this interval in the graph.
If you want I to be the ending of this component,
Yeah.
you must find the maximum index such that this interval doesn't intersect with the ith one.
So you mean that if this is the ith interval and I want to, this is the last of this component, the last ending, so I should find what?
You should find this interval is the last of this component. So
Yeah,
you
yeah.
must find the maximum index such that maximum index j such that the interval j doesn't intersect with I.
And then how can I update that? So consider it's one of those intervals.
Yeah, then this is dp of j, k minus 1.
And I can have a plus one for having this interval too.
Yeah, of course.
And there exists only one of these. So by this you mean that this jth interval belongs to another component, yeah? So this is the idea. But we should consider all of different intervals that does not intersect with our interval. The reason is that the answer might be greater and also you miss something. And by having the jth interval as the end of my second component, is this the maximum value of intervals that I can choose? Maybe I have an interval here. So to have the maximum value, I should choose this.
Or dp of I minus 1, k.
No, in the dp of I minus 1, I didn't have this interval. Now I have this one, and I might have this one too, and go for the j in the second component.
Oh, but if you saw you said that we saw the ranges by ended.
Yeah, yeah.
So there is a range that is going to be the transition dpj for each j that ends before.
Yeah, it's a range. These j's are the range that are less than the start of this one. Yeah.
You have also the range that intersect. You need to complete the answer in that way.
Yeah, I should add some value too, but we haven't yet figured out what is the value now. Can you say that? No, it's not. Basically, the answer is that if I want to have interval j ending as the end of my second component, if I now want to have the maximum number of intervals selected, I simply should select all intervals after this point, all intervals starting after this point.
But you need to ensure that they are in the same component as the I interval, right?
I can somehow change my constraints that I have at least k different components.
Okay.
And by that, I don't need to ensure that all of these form a component or not. Simply, I should, for each of these, count the number of different intervals after the ending of j that also their ending is less than my ending too. I mean their index is less than I. So I can basically find this number using a segment tree. With simply, I'm moving with the intervals through their endings. Whenever I meet an interval, I add my segment in the interval's beginning index. I add that index plus 1, and this index, if I sum up all my segment values here, it becomes the answer that I should add to this DP. But yet the complexity is not okay. Yeah, I find the best prefix for j. Yeah, the idea is like this. That the problem here is that I cannot iterate through all different j's. So basically, the idea is to also store these dp values in a segment tree. I mean, if I find this value, I store this value in the segment tree at index j. And also, I can update this value too. Whenever I see an interval coming, I can add value of all of the previous dp's. And by adding this value, finding the answer to my dp is simply taking the maximum j, which the ending is less than the start of the ith interval. So simply finding that value, which I call mx here, is querying my segment tree to find the maximum value in a range. And hence my dp value becomes the maximum of these two.
Aren't all queries from 0 to the j that you count?
What? Yeah, all of the queries are finding the maximum between 0 to the beginning of the ith interval. Yeah. So the queries are easy to calculate, and I can update them easily.
I think that I got it. The part of avoiding the range that intersect with myself, with my interval that I'm seeing right now, you just, to avoid that, you change the IP definition to the IP of ik. That means I have at least k. Right?
Yeah.
And by doing that, you just don't look at the intersection, at the intervals that intersect with myself.
Sorry, can you repeat?
Yeah. I have the interval I, which is the one I'm seeing.
Yeah.
Okay? So, and I want to compute dp ik.
Yeah.
So, by doing this, this idea of GP to at least k components,
Yeah.
you can ignore the previous intervals that intersect with myself, right?
Yeah, I will ignore that. The problem was that if I have a j here, there might come another component here that doesn't intersect with my interval. The problem was that if I add these intervals too, there will be another component too. So basically, I was choosing all of the intervals, but there might come an added component to my solution, or maybe more. This was the problem. So I was not avoiding intersections, but I was doing this to handle these added components. But we can see that in the optimal solution, when we consider this one as the update value, as the j that we update from, this will give us the answer. So basically it contains our answers. So if there is no question, I will go for problem D. So the problem said that we have a ladder and we have some points that we swap. At first we have a permutation 1 to n written in the up, and we go down and swap two elements whenever there exists something like this. And we go down and we will encounter another permutation. So, and the problem was keeping the minimum number of these swaps, that the outcoming permutation will be the same. My solution to this problem, I don't have proof for that, and if you find a proof when I'm telling you, please tell me. And also, so let's talk about it and we figure the problems after that. The idea behind solving this problem is that when at some point I swap the number I and number j, and in the next, after many steps, I swap these two numbers again. At the first one, I is before j, and at the second one, j is before I. Because if they want to change their order, they need to be swapped with each other. I can see that if I have these two at some point, I can greedily remove this. And the answer will be the same.
Remove both of them?
Yeah. Because the path that this I, after swapping I mean after that this I is here and this j is here, the path that is goes here, and the path that this j1 goes here. If I remove them, they will both go in the same path, and at this point they will be again I and j. So removing these two doesn't affect any other things. And it doesn't affect other numbers because they are simply swapping by something, and now they are swapping too. My guess was that if I do this greedily, it will be correct. And it turned out that it was right. I want to say that I participated in this contest myself, and because of that, and the organizers didn't tell me the name, and because of that, this contest didn't have any name, and yeah, I accepted with this idea. Can anyone give a proof for this?
Even if I or j appears in some other swap between those two,
Yeah. I have some observations for this case of the proof, but I don't have an exact proof for this one. My observation is that if you consider all of these sets of ij values, they form some swaps in the process. And my observation is that if I only consider these values, removing at the end, I will remove all of the pairs, and only at most one swap between them will exist. And it doesn't matter the order which I remove this. The thing that I should say is that after removing these two, do I affect the other values of x and y's that were supposed to be removed too, or no? So if you find this, the problem is that when I remove this, maybe some x and y doesn't work with them, and maybe with some I and y doesn't work, and how can I ensure that works? If none of these two values are equal to I and j, so this removing these things doesn't affect any of them. So basically I can say that this the problem of removing some possible deletions comes when I have a value in the xy equal to I or j, which they were possible, and after removing they might not, because consider I had between these two I had an I and y here, and I had an I and y before. After this I'm going to ruin this thing, because this will become the j and y. But the observation here is that this won't come alone. If I had I and y before this, and then j passed through the I mean here consider that I had y and I, because the I then came left. So I can say that at some point j passed I2, j passed Y2. So if these things is happening between these two, if there is a swap here and I had a yi here, if the j, I had a yi and I mean I had a iy here and some j is going left of I, so it has passed the y2. So I somehow have the value of yj here too. I think, I'm not sure that these values will be common, and if I then replace the I and j in this interval, because of this fact that every element passing through this have effect in both of the values, I can say that this will be a match for another one and the other match will be okay too. But I'm not sure. It's just an intuition that why this could be right. So this was the idea. The question is that how can I implement this? I have personally many implementation issues with this problem, because I cannot do this in one pass and one simulation. The reason is that changing these values sometimes requires me to restart from the beginning. So the thing that you should take care is that for each pair of values I and j, no, I'm not sure, but what I did was that every time in a simulation I only deleted 2 of these. I don't know whether it fits in the time or no. Let me see the limits. We have like 50 poles, and we have at most at each of these we have 1,000. Swap, and I think what I said was basically doing the whole simulation at most this time, but it's a lot. I don't know. Anyone has any idea to improve this?
Stack for each column.
Yeah.
So when you have a consecutive pair in one column, you look at the top of the stack, the 2 columns next to it,
Mm-hmm.
and see fast if there's something in the middle.
Mm-hmm.
If not, erase the cell bit. So if you go for like the higher ones,
Mm-hmm.
you can do it once you
Uh-huh.
right, so
But yeah. Yeah, the problem is that those 2 swaps of 2 numbers may not be in the same column. They might be, I mean, there might be a swap here of ij and swap there. But I don't know, you can try to see what happens by doing these things, but you should take care that by erasing you cannot necessarily do the right thing after that. You should update all other values too. By that I mean, for example, you had 1 going here and 2, and then somehow 2, we have 2 here and 1. I mean 1 here and 2. And after that, the values here will change. The value of the pair that are swapped together. If I remove this, instead of 1, this should be 2. I should take care of this. But I got accepted using simulation every time. I don't know, maybe the test data was big. Any other problems from this contest to solve?
Can you give some ideas about problem G?
And what was the problem?
Was one about you had points, colored points in a line. You wanted to keep a set of points, and there were some rules about the distance between points in the set and in the complement of the set.
Just problem G.
G, yeah.
I don't remember the problem. If anyone knows an idea for this problem, please say.
My idea was with E solution, we use the standard tree to arrange them.
Please.
Okay, so you have stones on a line, different positions, and you have groups of stones with the same color. So my idea was to keep a DP on each stone that stores how many stones do I need to put to solve this prefix, right? So to do the transition on the DP, I had a few constraints. For example, suppose I want to transition to the previous group of stones. I want to make sure that first, the first stone in my group is closer to me than to that other stone, which is going to be the last chosen one in this group, right? So you can do the reflection of this stone from this stone. Reflection. It has to be left of that, right? And then you had another constraint, which was that this stone must belong to this group and not this group. So if you do the reflection of this stone by this stone, it had to be left of this, right? So you have two constraints, and you need to do the transition towards this group, so that's another set of constraints. So if you take the intersection of those two intervals, you get a new sub-interval. And you know that the transition, if you want to go to the other group, the previous stone you selected was in the previous group, then it must belong to this interval. So you just do range minimum query in that interval, and you continue with your DP. The other possibility is that the previous selected stone was in your interval. And in that case, you just do a range minimum query in this part, right? And well, that's the DP. return the answer for the last value. Okay. Sorry, not for the last value, for the minimum, the last interval, I think. Okay. Any questions?
Can you give some clues about problem C? The one with the arrow?
I didn't solve problem C during the contest, and I haven't solved it yet. So if anyone can help me, since I saw that many teams get C accepted, I didn't think twice about it. Anyone can give the idea of problem C? Anyone? So I will think about this and I will tell you whenever I solve this problem. So today I wanted to talk about polynomials and generating functions. And also, I like to talk about polynomial transform. But when I was looking for the problems that I have, I saw that many of you are familiar with these concepts. And I'm not that strong in polynomials and especially generating function, but we can talk fast about them and see what can we do with them. So my reference for polynomials is a website. That you can go and see the details of what I'm going to tell you, and it has a lot more detail. So I feel since you are familiar with the Fourier transform, you are familiar with the polynomial and multiplication, and I want to ask you the question that how can I find the inverse of a polynomial? Sometimes with doing some things with polynomials, we need to able to calculate the inverse fast, and because of that, we need a algorithm to do that.
This is the quotient of the polynomials over xk.
Yeah. Let's say that I have the inverse modulo x to power of a. For example, if the power is 1, if a is 1, then the p minus inverse of p is equal to, if a0 is the constant factor, it will be 1 divided by a0. The idea is, if I have this, I will name this as b of a. Can I find the b of 2a? I mean the inverse modulo x to power of 2 multiplied by a, or no?
The polynomial coefficients are integers.
Yeah, they are integers. They are, I mean, integers. Yeah.
1 over a0.
It is, if I'm taking this modulo x only x. I mean, I can divide polynomials and I can have remainder of them.
Yeah, but the coefficient of the polynomial, you said it was integers, right?
I can have it in the. I can have the coefficients in, for example, in the problems that I have seen, modulo prime.
Okay.
Yeah.
This is just the inverse of
Yeah,
a0.
just think that, it's the inverse, and just think that all the things, all the coefficient things are going modulo prime.
Okay.
So because doing these things in the double field, it's not a good idea, I think. It won't help us solve some problems with polynomials. So I can just like guess that this will look like something like this. I should find a polynomial c, which now multiplying this by my p give me the right answer. I mean by that, p of x multiplied by a I also know this one. and that BA is the inverse modulo x to power of A. And if I take the modulo here, by knowing that fact, I will by that I can see that no, it's wrong. Let me check. So, since I don't know the exact thing, I will skip this because you can read it yourself. But we can have this simplified result at the end. That B of 2A is B of A. And minus P of X and so if we want to find the inverse, we can find it in log n step, and at each step we are performing a polynomial multiplication. Which will take the order of n, and I think the whole complexity is n log n. And so we can find the inverse in modulo a prime that we had for our factors. And now there is another thing that I want to mention in polynomials, which is the fact that somehow computing the polynomial is not easy. It may take time. And we can compute the value in some points, but we cannot move them to the Fourier space, the frequency space for Fourier transform. We can simply calculate the value of polynomial. If the polynomial has degree n, we can calculate the value for n plus 1 different values. And we can then, having these values, interpolate the answer, the polynomial back. And this might be a faster approach than computing the polynomial itself. It can be proved that if I have n plus 1 points of a polynomial with degree n, I can find I have only one polynomial corresponding to that. So, having n plus 1 values, how can I find the polynomial? We can use a Lagrange theorem which states the polynomial if I calculated the value for x1 to x0 to xn, and I have found the values, these are the answers. I can see that if I can compute this polynomial, this will be the polynomial corresponding to these points. And why is it true? If I know that for each n plus 1 points there exists only one polynomial, if this polynomial has only the right values as at these points, I can say this is the right one. So I can calculate this value for a given value xi, which I know the result should be yi.
J must be different than I am.
Yeah, here j must be different. Here I can see that in this sum of I, if I go to another I, consider it's k, I'm going through a sum here of i's. If k is not equal to I can say that the value will become 0. The reason is that if k not equal to I have something x minus xk. So this will be equal to 0, and the whole thing will be equal to 0, except I have k equals to I, and in this way all of the values will become xk minus xj divided by xk minus xj. So they will cancel out and they will be 1 multiplied by yi, which here is yk. I will get the yk as an answer. So if I calculate this polynomial, this gives me the answer. So how can I calculate this fast? A naive implementation will give me, I think, for each of these I should multiply n things. Here I should multiply n things as well. And I should find the reverse too. So, here multiplying n things will take n to power of 2 time, and finding the inverse also take, I think, n to power of 2 log n, if I'm right.
Are those like numbers?
These ones?
Yes.
Yeah, I can choose them randomly for what values I like. I have calculated them before. These are like numbers in the modulo p, a prime number.
You can pre-calculate the denominator and get rid of the log n.
You mean that I pre-calculate this one? How can I?
If you want for the
Yes.
you
Yes.
can multiply by.
Yeah, I was wrong. I can calculate them, and I can do this in O of n.
Yeah.
And
Yeah, I can calculate this.
The,
How fast?
the denominator it will take n log n. Well,
Yeah.
you will do this only once.
How? This is different because it's xi minus xj.
yeah, but you have at most m different values.
Values.
So you just pre-calculate every inverse, and then you just check.
So this will be O of n finally.
Yeah, and you have to do this. But to actually build the polynomial, you have to multiply this by n, right? Because
Yeah.
you still need to check every pair, I and j.
Yeah.
But you can after building the pair, you just check what you recompute the.
Yeah. I agree. But it will take O of n, and if I'm just talking about the naive solution, and at most this operation will cost O of n to power of 2.
Yes.
And what about the upper side? Since it's multiplying the polynomials, it will take a long time. And I think in total it will be, each of these multiplications are in the order of n to power of 2. I think totally it will become order of n to power of 4. Because whenever I want to multiplicate, I need to do like a n squared approach. If I'm not using FFT, so it will take in total n to power of 4, but I can make it better.
But multiplying by a monomial is linear.
Oh, so you're right. How is it linear multiplying two polynomial?
A polynomial by a monomial.
Oh, you're right. So it's n to power of 3. Yeah, you're right. But it's still slow. I can do this a little faster by doing a divide and conquer approach. So if I have the polynomial p equals to x minus x0, what is the derivative of this polynomial? It's like for each of them, it's like the sum of I multiplying by all j not equal to I, x minus xj. Am I right? And basically, if I calculate this polynomial, I can find the derivative easily because I have the factor, I have the coefficients, and I can find this one easily. And I say that the derivative of xi now equals to so I can find the value that I have below here, which was xi minus xj, equal to, I can find all of these will equal to calculating at point xi what is the output of this polynomial. And it will take, I think, a linear time. So I can calculate this value for all of them in linear time. And I will solve the whole thing, finding the whole value by a divide and conquer approach. First, for each of i's, I store this value. I want to do a divide and conquer and build up the answer.
What would be the final complexity?
I think it will be n to the power of 2 log n.
Okay.
If I'm right. Because just calculating these values will take n to the power of 2. And after that, how can I build this? Consider that I have yi and I have yi plus 1. Now I want to find this value here, which I mean by only having these two values. What will become the upper part of my polynomial here? I mean by that, this one should be multiplied by this one should be multiplied by x minus xi plus 1. This one should be multiplied by x minus xi. I mean by going up, I want to find the value of the upper part of my equations correctly multiplied by all of these. So if I have at one node one child corresponding to indices between L and R, L and M, the other one between M and R. If I multiply this value with this multiplication, and if I multiply this value, this polynomial with this one, I will find the right value here. And I can store the values for all of these, like I can store the value of this. This is like a sub part of my polynomial P of L and R. I can store the value for all of these in like O of n to the power of 2. And I can simply then multiply the answer of this by P of M and R, and here by P of L and N. And then build my answer up, and when I go to the root, I have the polynomial, which is the interpolated polynomial of my points. And the whole complexity here will be if I'm right, at each step I have a 2 polynomial multiplication, which will be O of n to the power of 2. And at the end, I think because I have log n steps, it can be proved that it's O of n to log n time. And it is a faster approach. So, knowing all of these, sorry that I'm not very expert as binomials, I will solve a problem regarding polynomials too. The problem says that I think the problem said that we have like n wizards. Each of them has a power magic of pi and has a value of OI offerings to sacrifice. Let me skip the story. The problem is that we have gave you this. We want you to find the minimum positive and integer x, which this holds.
You want to find what?
The minimum integer x, which is greater than 0.
Oh, it isn't true.
Yeah.
How large is n?
I will tell you now. I think the pi was like up to 10 to the power of 15, and OI was up to 10 to the power of 9. I think it was the constraint. Let me check. I was wrong. It was the reverse. No, it was right. And also n is less than 1,000.
Is the minus 1 on the index where x to the power of O?
No. This is like this. And
Is that modulo something?
Yeah.
is that what?
Modulo something?
And let me check. I don't think so.
PI and OI are all positive.
OI is positive, but the PI is not necessary. And also,
Pronto, não precisa ter pergunta.
Tá estranho, viu?
Why do we need this -1 in the exponent of x?
I think we should use this. it's simply the derivative of another polynomial. Am I right?
Entendeu? Pra poder integrar depois.
Should be greater than 0 because in that case,
Yes, you're right.
like it should be greater.
Yeah, let me just check the.
Só porque ele integrar depois tipo pro e passar por esse point.
Não, entendi.
Então, você só pra poder exponenciar entendeu?
I think the problem, you're right. This, you can consider this is right.
Tem uma coisa estranha. Não é difícil, não. É muito doido. Eu olho pra cima todo dia. Muito.
Mas eu tô
Não, eu não.
I think you can go for a break, and after that, we'll solve.
Eu acho que no mínimo uma ligação found it, but something doesn't sure it's found by something. Você não pode confirmar. But it tells you the tells you it's found it, or you have to prove. Por causa da geometria. A geometria do coelho. Não tem como fazer. Por causa do jeito que está desenhado a barra. Nem sei o que acontece igual é Então, esse daqui.
Más o menos como es el estado. El problema es
So now let's continue the problem. The idea to solve the problem is that first consider that we like have this is like a p of x. You can see p of x as a an plus a0. If a0 is not equal to 0, we can say that if r is a root of this polynomial and r is integer, we can say that r divides a0. The reason is that just place r instead of n, we will find that r multiplied by n a n r to power n minus 1 and so on plus a0 equals to 0. So moving a0 to the right. Since all of the coefficients are integer too, we can say that with this r divides a0. And in our problem, we will see that this simply tells us that for minimum OI, if the root divides the minimum I, which is not 0, because if the minimum has a x with power more than 0, we can divide that by x, and we can simply deduce this one. So, knowing this observation, how can we solve the problem? The answer is that we should iterate over all possible divisors of these two numbers. But in order to iterate over them, we first should factorize these numbers. I can factorize P, I can factorize O easily, but how can I factorize P? Sorry? The square root is quite a lot, and we have many test cases. No, we don't have many. We have only one test, and I think it's a lot somehow because it's like going 3 multiplied by the 10 to the power 7, and each step we should perform I think a costly computation, which is checking that whether that number divides the number we want or not. Yeah, that works. That's basically an algorithm that I forgot. Can you tell what was the order?
Fourth root event.
Sorry?
Fourth root event.
Uh-huh. So there exists an algorithm that can solve factorization with this complexity, but it's not required here. We can do some more simpler tricks.
Just test the primes until square root of p, and there are at most square root of p divided by log n primes.
Uh-huh.
As simple.
Yeah, maybe only by considering the primes up to this value and then going for them to them, because the values are, because the primes are like primes up to n are like n divided by log of n. It's relatively lower than this number we can do. But what else? Do you have any other idea? don't have any idea, but in my code, I have done something strange. And I will tell you, but I now can't understand why that was right. The thing that I have done here is basically going only through numbers up to 10 to power 6 and check whether the prime divides the number divides out this number or no, this pi or no. And if not, I only got like a square root of pi, and I only checked this value minus and plus 10 and checked whether this x divides pi or no. And it seems, and the code got accepted, but I don't know why. I don't know. I mean, it's wrong. I think it's simply wrong. But I sorry. Now let's talk a little about generating functions. Generating functions is simply another way to solve some counting problems, maybe faster than DP. I mean that every problem that we solve with polynomial functions can be solved with dynamic programming, but slower. And using this generating function has two benefits. One benefit is speed, and the second one is that you might be familiar with some generating functions for some special counting problems. Like, for example, I mean by that, by generating functions, I say that I have a problem which has an answer for every number x, for every number k. The answer is ak. And I will correspond this sequence with this polynomial. This is one of the representations. It's simply a generating function. We might sometimes correspond to another polynomial, which is ak divided by k factorial multiplied by x to the power of k. And it's like an exponential generating function, because we can sometimes show this by e to the power of a. you can take this as a simple symbol for that, and it's basically the Taylor series of this one will become this. I think consider this as a symbol. If I'm right, I'm not sure. But if we have this one, we can see that it's like this. Am I right? If I have this one, it's like this one. By that I meant that we might do some operations which might come handy in this way. Because taking derivative of this one is like simply the derivative is itself, but we can do some things and we will see that this may come handy. But let me here, I don't know how to show this in terms of value, but sometimes you store this like this. And some famous things are like the sequence of 1, 1, and so on. In the first representation will look like which is basically equal to 1 divided by 1 minus x. These are some good things that we should consider. And like, can someone says what is the representation of this one? Can someone say that? How can I represent this?
X over 1 minus x squared.
Yeah. It's, if I'm right, is it right?
It's an x.
Yeah, it has an x. The reason here is that the basic thing that we should know is that I could have obtained this one from this one. By taking derivative of this polynomial, I would, what I have here, if I take derivative here, I have like k x to the power of k minus 1. Am I right? And if I have this one and I might multiply this by x, I will get the same thing that was here. So taking derivative of this one multiplying by x lead me to this one. So I can take a derivative from this one, which will be 1 divided by 1 minus x to the power of 2, and multiply this by x. So the good thing with polynomials is that I can use the final form and somehow combine them and take derivative of them. There are some important other things to know, and one of them is if I have this polynomial, it represents And there are many other things. But I can have binomial coefficients in my polynomial too. Like if I want to have the sum of k of n x to power of k, how can I write that down? Yeah, it's simply 1 plus x to power of n. So it's exactly the binomial coefficients that we have. By having power of k, we have k we have to choose k out of n different x's here. So basically we can build our sequences using these ones. And also we can do another tricky thing. Which sometimes become useful, and is when we have a recurrence relation. Like we can also express this in terms of polynomials. By this, if I have the polynomial of a, I can say that p of x now equals to 2 multiplied by p of x Now maybe having this can solve my polynomial, my recurrence relations. So this is the whole thing about. I think after that, the only thing required is to try to express things and count things using polynomial. I will now solve a simple problem. There are also in some problems we need to find the polynomial and then solve a problem using transformations like Fourier transform, because when we have polynomial we can multiply it fast using Fourier transform, and it depends on the problem. Unfortunately, every problem I had, everyone has accepted the problem before, so I couldn't put any problem in contest, sadly. So let's solve a simple problem to see how this works. This problem that I'm going to tell you has simpler solutions too. The problem says that you have a garden with flowers. You purchased n boxes. Each box has the ith box has fi f of ith flowers, which all of the flowers are the same, and all of the flowers of different boxes are different. Now we want to count the number of ways we can choose only S flowers out of all of the flowers and plant them in the garden. And the problem says that what is the answer? Count the number of different ways that we can choose this. The problem said that we have n boxes. Each, the ith box contains f of ith flowers of the same type. All different boxes have different flowers. We want to now select exactly n flowers out of all of the flowers and plant them. How many different ways can we do that? And n is less than 20, and I think f of I is less than 10 to the power 7. Oh, 10 to the power 12. Yeah, you're right. Let me check that. The value of S is also large, 10 to the power of 14.
Does the order
Not so much, I think. Just in taking a combination, maybe.
If you plant 1, 1, 2 is the same as planting 1, 2.
Yeah. We're counting different sets of them. One can solve the problem easily since n is less than 12 with inclusion and exclusion principle. I'm telling you the other way that I'm not going to talk about. By that, we can take S out of all of the flowers and see how many different ways we have, and then remove the ones that we counted again, and so on. We can use the inclusion and exclusion principle, and for every mask of boxes, then remove or add something to answer. But here, in terms of generating functions, we can see that if I have 2 boxes, right, the first box has only 2 flowers, and the second box has 4 flowers. The answer of choosing 3 flowers is simply taking the coefficients of x to the power 3 of this multiplication. So, because every number in this means selecting I from this one and 3 minus I from this one. So so I have like n polynomial. Each of them is 1 through x to power of fi, and I'm like want to multiply all of them and find the answer. So can I find for this polynomial a simpler representation like this? And what's that? I can see that if I name this one, if like it's to x to power of 10, if I name this polynomial with p, I will see that, yeah, if I multiply this by x and add 1 and also remove x to power of 11, it's equal to itself. So I can do something and it will become p is equal to 1 minus x to the power of 11 minus x. So I can represent these polynomials with this and replace 11 with fi plus 1. And now I should calculate the multiplication of these elements. And I can see that here this will become the whole thing divided by 1 minus x to the power of n. Since the n is small, I can find the upper side with using like 2 to the power of n operations. What? Because n is small, I can do this. It's not necessary to do that. But if n was large, I should have to do that. And there is another polynomial which I should calculate, and then how should I calculate this one? What is this actually? I have told you that before. It's like this one. It's like choosing I and yet I don't know how to solve the problem. What should I do?
You have the series for the denominator.
Yeah.
Then there are at most n polynomials multiplying with 2 coefficients. Then you can brute force multiply them to get to the power of n coefficients.
then you can just make a convolution to get the coefficient of the multiplication
Yeah,
of those two.
yeah, that's right. That's right. Basically, I will, for the denominator, I will have this polynomial, but I don't need to calculate this exactly. I want to, after all of this, find only the coefficient of value s. And since the degree of this polynomial is low, I can brute force on these values and find this, only calculate this number according to what I need. I mean that these has at most 10 to the power of 6 degree, yeah. So after that, all of the coefficients are 0, and I'm only interested of I remove this one, and it's like multiplying these two. And since I'm only interested in the coefficient of x to the power of s, I can perform a sum. A sum to see if I have x to the power of I in the left side, and then I will have x to the power of s minus I in the right side. I have the coefficient here, I don't know, b. I can calculate this one and just find the answer.
You said the degree of the left polynomial was 10 to the 6.
At most, because these are 20 at most.
Yeah, what you meant is that only 10 to the 6 coefficients are non-zero.
Yeah.
This is not the degree of the polynomial.
The degree is like very big.
Yeah, you're right. It only has 10 to the power of 6 non-zero degree. Yeah, you're right. And the problem is solved this way. Also, in your first day contest, ICL 2015, you had a problem which could be solved with polynomials. The problem was that you have a convex polygon of size n, and basically it's a chocolate, and I can cut this, and I want to count how many cuttings I have that produces exactly k triangular parts. I saw that one team solved this problem, and this problem is also, we can solve this with dynamic programming, but we can solve this with polynomial a little easier. And also here the n was less than 300. I have a solution but haven't tested my solution, so I will tell you, and if it's wrong, please tell me. And I'm not sure whether it's right or not. Consider that we want to finally have a polynomial like named, I will name like f, which the kth coefficient is the answer. Basically, f for each x to power of k has coefficient of number of ways that I can have exactly k triangles. I will now write my f. I will call this f of n, since it could be different, and I will call this as sum of g of n plus h of n. And these two will correspond to these two states. That's whether there is an outgoing cut from the first vertex or no. The G1 counts the number of cuttings with having a cut from the first vertex. And the H1 counts the number of cuttings without having a cut starting from the first vertex. I can write g of n equals to choosing the leftmost cut, and if I choose the leftmost cut at the index I here now have a polygon of size I minus 1, I think. And to solve the number of these ones, I mean to see the number of countings, number of triangle parts in this one, it will be like h of I minus 1. I think it's I. And the rest, how much is the rest? The rest is f of n minus I. These are polynomials.
What? H? Isn't that F?
It's h, since in this polynomial, since it was the leftmost cut, I don't have any cut from the vertex 1. I should count this one really carefully to don't count same thing twice. But in the other side, I might have a cut, outgoing cut from vertex 1, or I might not have. So this will be f. And basically this is the multiplying these two polynomials. Because basically I want to, for having k1 here and k2 here, I want to count k1 plus k2 in the whole polynomial. So this is the g. And h is a little more complicated. At least my idea for it is a little complicated. I can say that if I don't have any outgoing cut from the vertex 1, I somehow can merge this one into these sides and have only one side here. Or somehow I can say that it's the f of n minus 1, but I'm counting something's wrong. And I'm counting the triangles formed by this virtual side mistakenly. So I should not count these triangles. And basically I count them. And how can I remove these duplicate things? I can fix if I'm counting wrong, so there should be a triangle here. I can fix this one. And if I define another polynomial p of n, which is the counting of this one, I mean I should choose the I. And how many cases I have here? I think, yeah, it's f of I minus 1. And here I have f of, yeah, I think I have something like this. But I should here take care that h of n equals to x multiplied by Pn plus Pn. Because in each of these states, I have counted a cutting in a one more triangle. So I should remove the one more triangle and at this state, at this cutting, at this specific cutting, to the cutting without that triangle. So basically I should remove this from the one more triangles, which is basically multiplying this by x, and then adding to the current numbers, to the correct number of triangles in the coefficient, in the column. And this way, this is all the polynomials that express the solution to the problem. For basis of this, I should fix the value too. For example, for f of 3. And after that, calculating this naively is likely doing the dp, and I think it will take the complexity of n to power of 4, because computing this one, this is I'm performing n times here. I have a sum n times, and doing this takes n to power of 2 times. It's like n to power of 4. But can I calculate this value for a specific x of I faster? I mean, for x of I, each of these will be only a value. So computing this one will take only order of n, and the whole thing will take the complexity of n2 for only one value. So if I take a modulo, the problem already has a 1, and calculate for a specific xi, I can do this in the order of n to power of 2. And since I know the answer to k is less than n, if I only find the value for n plus 1 point, this will take O of n to power of 3. Then I can use interpolation to find the polynomial back. And I can do that is O of n to power of 2 log n time. And I will find the answer polynomial, and then I will find the k coefficient. This is it. Somehow seems complicated, but the whole problem solving here is easier than solving the whole problem with DP. I mean, I basically solved this problem with a easier dynamic programming. But I could have found the answer using placing value into polynomial and interpolation faster. And this is the idea that we can use in problems. It depends on you which way you choose to solve the whole problem with dynamic programming or not. And
você escolhe, por exemplo, alguns pontos para variar muito só que quando você escolhe um outro, então agiu errado.
I wanted to tell you another problem which you can think of, but I'm not going to solve that. Maybe I try to put this problem into a contest I created last 2 days, training ground. I try to add this problem that I'm going to tell you to that.
Just a moment, just to make sure. Is the polynomial, is the degree of the polynomial at most 300?
No, I don't think so.
Yeah, because otherwise, how can you interpolate it?
Basically, you're by having n plus 1 point, you are interpolating the polynomial modulo x to power of n plus 1. Basically, modulo of this is the same, and since k is smaller, this works. It's a magic trick, like somehow.
Oh, sure.
Yeah.
So interpolating with n plus 1 points is just like interpolating.
Yeah.
Modulo x.
Yeah, you can simply deduce that fact.
Okay.
So the problem is that we call a graph simple if each of its components has at most one cycle. Your task is to count the number of edges belonging to cycle in all of the possible good graphs and labeled graphs. I mean, for all possible labeled graphs with each component having at most one cycle, count the number of edges that belong to cycle and sum this up and print this. And the problem also told you print this modulo p, which is not necessarily prime. And also, we know that n is less than or equal to 2,000. 3,000. The problem also said that we have at most 3,000 test cases. But for all of them, the modulo is fixed. You can think about solving this problem.
I missed the explanation of the problem, sorry. I missed the explanation of the problem, sorry.
The problem said that we call a graph good if each component has at most one cycle. And for each good graph, we count the number of edges that belong to cycles. And the problem says that what is the sum of this value for all of the good graphs? Yeah, for labeled vertices. Yeah. So I think our lecture is over, but they told me that we should take a picture here. Yeah. Now come here to take a picture.
We'll be on the steps outside.
Outside, sure.
Yeah.
Hoje, isso aqui é alinhado com isso aqui, ó. Que as coisas que você arruma,